Hello fellow problem solvers, so today I'm going to be doing a cool number theory problem from the Asian Pacific Math Olympiad 2004, problem number 1. I suggest you try this problem out for a minimum of 20 minutes, ideally an hour, but not more than 2 hours. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 10 minutes. So now, without further ado, let's begin. So, the problem asks us to find all sets S of positive integers such that if I and j are in S, then I plus j over their GCD is also in S. So now, once you play around, what's the first thing? If you try to say 7 and let's take 9, if they're both in S, then you will have 7 plus 9 over their GCD is 1 will also be in S. And then if you take this number, it's relatively prime to 7, so you take them again, and you can just keep on adding this number, and you will always have a GCD of 1, because the GCD of x and y is equal to the GCD of x plus y and y. So you will always keep getting bigger and bigger numbers. So the first thing you notice is you can't have the GCD of two elements be 1, otherwise you will blow up to infinity. And now with that, I invite you to take another 5 minutes and try to push the problem further. And here's the next sort of step. Now we have, say at least if we have one element, mind you, if we just do I plus I over the GCD of I and I is I, we'll get what? 2I? Oh yeah, we'll get 2I over I, so we will get 2. This means that 2 is always an element of S. And now with that, it follows that, well, we can't have any odd numbers. If we did, we would just have I plus 2 over 1, and we would just keep getting bigger and bigger odd numbers. So the first thing to notice now is 2 is definitely in S, because I and J are not necessarily distinct. And this means if S has something, it has 2 in. And now let's see if it can have 2 and something else. See, it has 2 and 4. Well, then it has 2 plus 4 over 2, which is what is going to be 2 plus 4, 6 is going to be 3, an odd number, and then we lose. Okay, but then let's say it has 2 plus 6 over 2. Well, then it has 4, and then we can have 4 plus 2 over 2, and then we have 3 again, an odd number. So now the question is, can S have anything other than 2? And I invite you to take about 5 to 10 minutes and try to work it out. Here's the next step. So the first idea that came to me next was, if there's a number divisible by 4, then we're done. We'll get an odd number, and then S will shoot out to infinity. Otherwise, if that means we have even numbers, and these numbers are only divisible by 2. And then say it's 2t and 2. And then we'll have this is equal to what? It's t plus 1. And now t plus 1 cannot be divisible by 4, but needs to be divisible by 2. And I was thinking, okay, now I have t plus 1 plus 2 over 2 is a number. This is t plus 3 over 2. And now this number also is even, but not divisible by 4, which then tells us further and further constraints what t can be. And I can maybe do some infinite descent kind of thing. But as soon as I saw this, I was like, wait, there's another thing. What's happening when we take 2? If you look at on the number line, we take 2 and we take some number a. And then what do we have? Some even number, 2 times a. Then we have a plus 1, right? And then we take a plus 1 plus 2 over 2. We're always taking the arithmetic mean of these two numbers. And at some point, we won't be able to do that. So now what's the easiest way to write this down? It's using the extremal principle. Take the smallest integer other than 2 that is in S, and now that we know needs to be even, and call that j. Then we have 2 times, call that 2j is the smallest one. Then we have 2 times 2j over 2 is equal to 1 plus j. And now what needs to happen? Well, this number, if it's going to be less than 2j if j is greater than 1, it's going to be less than 2j. But that's the case because j is the only other even number other than 2 in S. So this is true, and j isn't equal to 2. So if j was 1, then this would be 2. So no matter what happens, we get a smaller number, which gives us a contradiction. And with this, let's do a write-up. So the first thing we do is we say from I plus I over I is equals to element S. We have that if the size of S is greater than 0, then 2 is in S. And then we have if the size of S is greater than 1, then if there exists an odd number in S, we just say that, we take the largest odd, and then we have a contradiction, an even larger odd, which contradicts that S is finite. And if there exists an even number in S other than 2, take the smallest such number 2j, and we get to another contradiction, and now we just saw that we can find a smaller element, just like from other than 2, greatest smallest element, j is greater than or equal to 2 times j, and we have this is greater than or equal to 3, and we have that this element is in fact smaller. So now only such S is S equaling just having 2. This solves our quite nice problem, and it shows this sort of idea of, I mean, if you have like sort of a thing that's always getting smaller and smaller and smaller, pick the smallest one with such a property. The extremal principle shows it very nicely here. And as always, thanks for problem solving.